Okay, hello everybody. We are ready to begin today's afternoon session with Professor Elisa Ercolessi from the University of Bologna, and she is going to talk about quantum simulations for abelian gauge theories. So, welcome, Elisa.
Thank you very much. Let me start by thanking you all for, and the organizers in particular, for inviting me to give this talk in honor of Bal. And let me also say hello to Bal, that I saw him passing before. And just a couple of words before starting. I was a PhD student in Syracuse from 90 to 94. And that was really a great period. And it was the period when we started working on posets and their algebras that we discuss with the tools of Conson non-commutative geometry. During that period, I met in Syracuse excellent researchers and colleagues who are now also very good friends. And I think many of them are actually here and taking part to this nice fest. Those years were for me years of very intense learning and very lively discussion that, as most of you might know, happened at every afternoon in room 316. And that actually shaped my way of studying and making research really a lot. So for all that, I'm really very grateful to Bal for his teaching and friendship in those years and even now. So I'm really honored to be here. And let me thank, first of all, Bal for all his efforts and work in all these years. So what I'd like to do today is to describe you some recent lines of research that we have been doing in Bologna in collaboration with many other groups that have to do with the quantum simulation of abelian, and somehow I will say just a couple of words about non-abelian gauge theories at the end. Just to start with a very quick outline. And the idea that I'd like to outline you how we can go, when talking about simulation lattice gauge theories, how we can go from classical to quantum algorithms to simulate field theories. The main ingredient here that I'll try to discuss a little bit is a quantum many-body Hamiltonian. Let's say in contrast with what happens with standard classical simulation, of lattice gauge theories in which you usually use the action, okay? And the goal of all this stuff is to actually be able to perform simulation of non-perturbative phenomena, so simulations that are able to take into account non-perturbative phenomena, and also describe dynamical or out of equilibrium phenomena. So the first step in all that will be the calculation of the many-body ground state of the Hamiltonian with sufficiently high precision. And that can be done either by a fully, let's call it digital or hybrid, as I will describe you, variational approaches that can be implemented on quantum computers. And I will comment on that at the very end. Actually, the idea of using quantum computers is quite old. The first time I think people talk about that was by Feynman in a seminal talk and paper at the first conference on physics and computation at MIT in 1982. Actually, for the first time, he discussed the fact that we do need quantum computers in order to be able to do an exact simulation of nature, since nature is quantum. So he was the very first one who put forward the idea that we do need quantum computers to be able to do exact simulations of physics. And indeed, that was just the beginning of a long history of actually classical simulation of quantum theories on classical computers, including field theory and gauge theories that reached big successes. So we don't need to remember the whole great effort that have been made to simulate field theories and in particular lattice gauge theories on a lattice. But so this is an old story in some respect. So what's new about that? Why to care still about that? The idea is that now we are in the era which we are starting to see real quantum computers. So there are big companies like D-Wave, IBM, Google, and so on that are really building and putting at research disposal platforms that are able to perform quantum computations. And but the same is actually happening in many research labs worldwide in academics, as well as now we have startups like the one that you see here, Pascal in France, for example, that was founded by the Nobel Prize Aspect a few years ago, that are actually putting on the market quantum computers. So the idea is, what can we do with that now? And this is actually a very exciting field at the moment, because it's actually putting together different ways of looking at the physical theories. It's putting together high energy field theory of fundamental interactions, for example, with the study of quantum many-body Hamiltonians on discrete space, therefore on lattices, together with the physics of synthetic platforms that are using, for example, spins or cold atoms and ions as platforms where to actually make the simulation, the real simulations. And these platforms are actually very versatile, and so they can be adapted for simulation of very different models. There is a lot of efforts, for example, to make simulation of chemical compounds and condensed matter models, which somehow are the natural ones to consider, but also more complicated statistical mechanics models and critical phenomena can be tackled from this point of view. And as I will try to convince you, and there is also a lot of research in that field, fundamental interactions can also be studied in this context by looking, for example, at particle physics or even gravity. And this is, for example, a review paper that came out a couple of years ago, and the idea is that these techniques will allow us to consider non-perturbative effects, to study, to simulate non-perturbative effects, together also with real-time dynamics and out of equilibrium situation for these models, which is really the new frontier of these fields. So here in Bologna, we started in collaboration with many different projects on that. I'm not going to describe them all. I just want to say that there is at least, worldwide and also in Europe, a big business about this stuff now. And so to start with, let me describe you the beginning of this story, as far as we are concerned, which resulted in a work in collaboration with Giuseppe Marmo and Paolo Facca and Saverio Pascacchio in Bari, and several other young PhD students and postdocs. And the first model we considered was actually a discretized version of quantum electrodynamics in one dimension, or the Schwinger model, if you want. And when I talk about one dimension, I mean one special dimension plus time. We are using a Hamiltonian approach, so time for us will always be continuous. And what we really need to do is, first of all, to discretize on the lattice the continuum Hamiltonian of the Schwinger model that you see here, which has a U1 gauge group. And it contains, as you can see, the standard electromagnetic energy, which in one dimension is just given by E square. And then we have the coupling of the matter field psi. We're talking here about spinless fermions. I don't put the spin, it can be added if one wants, with the gauge potential through the standard covariant derivative. And of course, you also have to take into account Gauss law. Then, as usual, we discretize time. We do not discretize time, we discretize only space, which is replaced by a regular lattice. And as usual, we have fermions defined on lattice sites, whereas the gauge fields will be defined on links. So also, let me start from the gauge fields, which are easier. So the electric field will be defined just on a couple x+1 of sites. And this conjugate variable will be considered, that we consider here, is actually the exponential of the gauge field A, which is what we call the comparator. And whereas the fermions, as I said, are put on the sides of the lattice, and we are using Schwinger's staggered fermion suggestion to avoid problems like fermion doubling, for example. So we actually split each physical site J into even and odd site x+1, on which we put the positive and negative energy solutions respectively. So in this way, each physical sites contain 4 states. The Dirac vacuum, in which we put a charge only on the odd site, which is occupied by negative energy solutions. Then we have the quark, what we usually is called the quark in the literature, which is by putting a charge on the even site, positive energy solution. Then we have an anti-quark by removing the charge from the odd site. And then we have the meson, which consists in a quark, anti-quark, or particle, antiparticle couple. So each physical site actually contains all these 4 states, which, if you want, are the basis of our local Hilbert space. Then we want to go quantum, okay? So let's describe what we have to do. And in order to go quantum, so to be able to also perform this calculation on a computer, we need also to discretize, but not only discretize, but also to make finite the degrees of freedom of the electromagnetic field that lies on each single link. And in order to do so, we go to a value quantization scheme in which we use the comparator, which is exponential of the gauge potential A, together with the operator that we denote here with V, which is exponential of the electric field, because the algebra of these satisfied by these two conjugate, this pair of conjugate variables is actually does indeed admits unitary finite representation of dimension n, which means that we can, on each link, we have a finite dimensional Hilbert space, which is generated therefore by n basis vectors, which on which we can act with V and U in a very simple way. The basis here, which is called the electric basis, is chosen in such a way that the V operator, therefore the exponential of E, is simply a multiplication by phase, which is 2 pi over n times k, whereas the U operator acts as a shift operator, actually a cyclic shift operator. So what really we are doing here is to substitute, to have a discretized quantum electrodynamics models in which we have fermions on the sites, and on the links we have an electric field which is characterized by a discrete and finite number of variables, which are given by 2 pi, by multiples of 2 pi over n, and therefore we have the then discrete lattice gauge theories. And if you work out in detail the Hamiltonian that you can get from the Schwinger model, it is the one that is given here. So we have the standard kinetic part in which the covariant derivative has been replaced by the U comparator operator. Then we have the stagger mass term due to the Schwinger approach. And then finally, we have the energy of the electric field. And let me just stress that we have 2 parameters in this Hamiltonian. One is a mass, and the other one is a coupling G of the electromagnetic field. And so the idea that with this Hamiltonian at hand, we are able to perform simulation in a classical computer. of different situations. What I would like to concentrate on is on some dynamical properties of this Hamiltonian, so some dynamics. And in particular, I will concentrate on the possibility to produce mesons, so particle-antiparticle pairs, and on the dynamical behavior of a string state. A string state is a state in which we create a particle out of the Dirac vacuum. So on the left, on the right, we have just the Dirac vacuum. We create a string, meaning that we create a particle on the left and antiparticle on the right. So we have a non-zero electric field in between. And we want to observe the dynamic of such a string for different values of the mass and the coupling constant G that was appearing here. Here is just a picture for Z3, for example. Okay, so let me just give you the result of our simulation. We did a simulation here using classical algorithm, in particular with the time-dependent density matrix renormalization group algorithm. And I'm just going to show you the result that we obtained for Z3, but we did the same for Z4, Z5, and we can just go on. And we studied two interesting dynamical problems. The first one is spontaneous pair production. So the idea is that we are actually using what we call a quench protocol. So we prepare the system in the Dirac vacuum, which is actually the ground state for very large mass of the system. And then we let it evolve freely with respect to Hamiltonian, which has some fixed value of M and G. Okay, which is not, so in this case, the Dirac vacuum is not the ground state of such Hamiltonian, and so it will evolve, and what can happen is that we have a spontaneous production of particle-antiparticle pairs, and that is indeed what we want to check. So the first graph that you see here is actually the average particle density of all over the chain. So, okay. So we start from 0, which corresponds to the Dirac vacuum. And then you see that as the time evolves, we have a non-zero particle density that arises from spontaneous pair production. And you see a first sort of linear term here, which is actually what also was predicted and studied by Schwinger in an old paper. And then you see that as time goes on, we see oscillation. So we have interference effects among the different pairs that are produced. And then we have all these oscillations here. And we calculated this quantity, because actually this quantity was measured in a very nice experiment using cold atoms. So this is an example of the very first experiment that happened in 2016, and then there are new refinements of that, in which people used cold atoms to build a quantum simulator for that. So just to see you that indeed there's experimental result using cold atoms as a quantum analog computers works quite nicely. And I also would like to show you some interesting results that we got by going from the weak coupling regime to the strong coupling regime by increasing the mass of our particles. And that, for example, can be seen by looking at density-density correlation. So by looking at correlation among particles. The first graph on the left, you see density-density correlation as they evolve with time, okay? In the case of a weak, in the weak regime, the mass is very small, very close to actually the confinement transition. And you see that the correlation starts to develop after a short time when pair production occurs, and then correlations will tend to spread all over the chain. On the vertical side, you have the size of the chain, following a sort of light cone direction, okay? On the contrary, when we go to very strong interactions, M here is much larger, you see that actually correlation are not longer allowed to spread freely inside the chain, and you see these recursive phenomena which is somehow also dictated by this oscillatory behavior that you see in the average particle density. So correlations are no longer able to spread all over the chain. They remain confined in the center of the chain, and they have this periodic, very strongly periodic behavior, which is something quite unusual to see. And these kind of unusual results come out also if you look at string breaking. And so what we really want to see is to see if we prepare the system in a string state to study if the string breaks into smaller strings as time evolves or not. And in fact, we see that we can see three different regimes, three different dynamical regimes by following real-time dynamics of the string. So we start at t equals 0 by preparing the string as a center of our chain. It is the color here represents the electric field. So you see that the electric field is concentrated only in the middle of the chain. And then when we are in the weak regime, M and G are both small, the system will evolve into a first phase in which we have a breaking of the big string into smaller strings, which are mesons, couples of particle pairs in nearby. Okay, and then interference effect will make this state evolve into a system in which we have two mesons at the end of a sort of light cone that we will spread moving toward the edges of the chain. This is what happens in the weak coupling regime. We have a breaking of the chain and spreading of the excitations. On the contrary, in an intermediate coupling regime, we do see a breaking of the string into smaller strings, which are couples, pairs of particle-antiparticles, but we do not see any longer the spreading of the excitations. And until we reach a very strong coupling regime, in which actually the string does not spread, but also does not breaks into smaller strings. So we are able, by following different dynamical evolution, depending on the regimes of the coupling constant in which we are. And that can be simulated very easily in this approach. So this is, as I was saying, done using our approach of a, let's say, quantum Hamiltonian on a lattice, but using just classical algorithm, in this case, the DMRG algorithm, to study time evolution of our system. Now I would like to move to describe what we can think to do on a quantum computer. Okay, and so I would like to describe you how we can actually develop quantum algorithm to describe the physics of lattice gate theories. And in this case, I will concentrate on the simplest one, which is just a pure lattice gate theory, so no matter added here. I will work in 2 dimensions, and I will take the simplest discrete group that I can think of, which is Z2. So in this case, our Hamiltonian is just defined on variables that are defined on the links, which are our field, gauge fields variables, which are just 2 states because we are looking at Z2. So I will take these 2 states as given by the plus or minus states of the X Pauli matrix. So this is a Hilbert space on each link, it's just 2-dimensional Hilbert space. And then the Hamiltonian we are considering consists of an electric part, which is just proportional to sigma x. So these plus or minus states are exactly the eigenstates of the Hamiltonian, of the electric part of our Hamiltonian. Of course, this electric part will contain the sum over all possible links in our 2-dimensional lattice. And then you have a magnetic contribution, which is built up as usual using plaquettes. And here we take the product of the sigma Z matrix, which does not commute with sigma x, on the 4 links that are making up an elementary plaquette that here I'm calling BP. So this is the standard way we write down the magnetic part contribution, and the total Hamiltonian is the sum of these 2 parts weighted by the coefficients h. And of course, we can also write down the Gauss law here which is just related to the application of sigma X matrices on all links. Okay, so this Hamiltonian, we know the analytical ground state in two limits of this Hamiltonian in two limits. One is electric field limit in which H goes to 0, and that, as we said, is just the tensor product of the state plus on all links. And we also know the exact ground state in what we call the magnetic limit, which corresponds to H going to infinity, because the Hamiltonian I've just described actually goes into the so-called toric Hamiltonian. And so the ground state here, the exact ground state is just an evenly weighted superposition of all possible Wilson loops, closed loops, applied to the electric field state. Okay, so these are the two reference states that we're using in the two different limits. And it is well known that the Hamiltonian I've just discussed actually has phase transition, quantum phase transition at the value of the H field, which is about 3, and that the system is described by a confined phase when H is smaller than HC, whereas it is in a deconfined phase when H is greater than HC, and indeed this is a topological phase. It is in the same class of universality than the toric code. And this is what actually we would like to check with our quantum algorithm. So the algorithm I'm going to propose you is known as QAOA, or Quantum Approximate Optimization Algorithm. And it's actually not a purely quantum, a fully quantum, but it is a hybrid classical quantum protocol. And we have decided to use a hybrid classical quantum protocol because the technology of quantum computers that we have at our disposal now seems to be more to perform better if you are using hybrid classical quantum hybrid protocols. I can discuss with that about that later, maybe answering questions if you have. And let me just describe it a little bit. The idea is to exploit the powerful of quantum computation to prepare the ground state of our Hamiltonian. So we actually have a quantum part in our protocol that uses a quantum computer for quantum preparation. So starting from some initial state, we use a quantum circuit, which is parameterized by some evolution angle that I'm just calling here in this picture theta, that will prepare for me a variational ground state. Okay, we choose which kind of variational ground state to prepare. We make up a quantum circuit that does prepare this state. And then we use the quantum circuit also to make a measurement of the mean value of the Hamiltonian on this parameterized quantum state, variational quantum state. And then we will update the parameters we use in our quantum circuit by optimizing the value of the energy, which means to minimize energy, using now a classical protocol. So we just use a classical algorithm to minimize the energy, and that will give us the better circuit that is actually able to prepare the ground state of the system. This is what is called the quantum approximate optimization algorithm, and it has been shown to be quite effective in some in different kinds of problems. And for the first time, we tried to apply that to lattice gate theories. So let me just sketch. Yes, sir?
You still have 10 minutes.
Perfect. Okay. And let me just sketch very quickly the steps of this protocol. I'm not going into the details. I can answer questions if you have at the end. So we decided to use as initial state either the electric ground state or the magnetic ground state, the two ones that I described to you. The second one is more complicated to prepare, but it can be done. And as you can imagine, it might be more efficient when we are in the regime of strong magnetic fields. And then once we have chosen the initial state, psi 0, either the electric or the magnetic state, here I'm just denoted with psi 0, we need to construct the parameterized quantum evolution, which will be then implemented by the quantum circuit. We use a Suzuki trotter-like decomposition. So starting from psi 0, we evolve it by using the exponential of the two pieces of our Hamiltonian, HE and HB, by making unitary evolution, starting from psi 0, at different levels. So use P levels. Here, P is an integer number that is denoting how many steps we are using in our protocols. And the rationale of all that is that increasing P, we will be able to explore more and more with better and better precision the whole Hilbert space by letting evolve psi 0 with more and more of these individual pieces. And the idea is that we are able to construct a quantum circuit, quantum gates, and a quantum circuit that are actually able to implement each step of this Suzuki trotter decomposition, so that we will be able to prepare this state by using a quantum computer. Just to give you an idea, the quantum circuit is very simple. If you want, when you want to implement the unitary operator that correspond to the evolution by means of the electric part. Here, the electric part is essentially sigma x, so it's simply the unitary evolution, which is exponential of sigma x, and it's just very simple circuit that needs to be applied to each state of each link, P1, P2, P3, and P4 for a plaquette, for example. The situation is slightly more complicated for the magnetic part evolution. We do also have a unitary operator, which is exponential of sigma z, but you have to combine the evolution of all links by means of this operator in a more complicated way, because we need to act on a plaquette, so 4 links all at once. And the idea is that we can evolve this, for example, this vertical link by taking into consideration what is the state of the other 3 links of the plaquette. So it's actually conditional evolution, which can, however, be implemented in not a too complicated way by means of this single gate unitary evolution plus conditional gains like C-naughts. And this is a picture, for example, of the evolution of 2 plaquettes like here. And so the quantum circuit can be prepared to construct the state. And at the very end, therefore, we end up with an variational ground state that we call psi p. We, as I said, evaluate the expectation value of the Hamiltonian, of the total Hamiltonian of the state, finding an energy landscape, which is a function of the variational parameters gamma and beta that I was describing before. And then we will use a classical optimization protocol to minimize the energy and find what are the best values of gamma of beta for the preparation of the variational ground state. The problem here is actually the energy landscape can be very wild somehow. It can be very rugged. For example, you can even have barren plateaus, which means that there are regions in which it is completely flat and it is different from zero, only very small region of the parameter space. And so it's not easy. So classical optimization has to be considered in a very careful way, but I'm not going to enter this result. Let me just show you some of the results that we obtained. The first thing that we checked was the accuracy of our treatment. Okay, and in order to do so, we did a simulation of our quantum algorithm on a classical computer. And in order to check the accuracy or the fidelity, we just calculated the overlap of the variational ground state, omega psi of p, that we calculated with the ground state, the exact ground state of the Hamiltonian that can be calculated by other numerical techniques. And what you see here, let me concentrate on the left, for example, is the infidelity, so 1 minus this quantity, as a function of different magnetic fields, H, values of a magnetic field H, different colors with the curves, and in how many steps are used in the algorithm. And as you can see that as we increase the number of steps, we do increase the accuracy of our algorithm, which is measured by 1 minus f. And of course, the accuracy gets worse as we increase the strength of the magnetic part if we start from, as we have done here on the left, from the electric field initial state, okay? But also when the electric field becomes 5, which is quite a strong value, the purple curve, you see that after 6 steps, we are actually able to reach an accuracy which is better than 10 to the minus 3. So it's not so difficult to have very high accuracy here. And once we have checked the ground state we have prepared is actually good, okay, we can go and calculate the physical quantities. So here, for example, I'm showing you the graph of Wilson loops. That are actually able to detect the phase transition, which, as I told you, happens at H around 3, because Wilson loop will start to go from an area low or region to a perimeter low region that correspond to the confined and the deconfined phase respectively. And for example, if you look at the big graph here, we are going to show the Wilson loop ratio as it is defined here, which is a good quantity because we don't have to worry about the non-universal constant that appear in front of the formula of the Wilson loop. And you can see very well that our result can detect the phase transition from an area to a perimeter low very, very nicely. And lastly, there is another last result I would like to show you. As I told you, in the H going to infinity limit, we recover an toric code Hamiltonian. So, and we are in the universality class of the ground state of the toric code, which is a topological model. Okay. So what we wanted to check is also the value of the topological entropy. The topological entropy is defined by choosing a 3 partition of a region. So we chose the one that is shown here. So the rectangle that contains these 6 links is actually divided into the 3 parts A, B, C with 2 sides, 2 links each. And the topological entropy is actually defined as is shown here, where S is the standard von Neumann entanglement entropy. In particular, the full von Neumann entanglement entropy is just the last piece, SABC, which corresponds to taking the von Neumann entropy of the full rectangle by tracing out the whole rest of the system, okay? And indeed, the graph here shows the result for both the entanglement entropy and the topological entropy. The topological entropy is the green line, and which interpolates very well from the 2 known analytical results, which are 0 when H is equal to 0 because the system is in a factorizable state, to 1 in units of log of 2. Okay, because in the toric code topological entropy is actually minus log 2. Okay, and as you can see, the numerical calculation that we do indeed reproduce this very well. Just final remarks. We are working now to extend these ideas to many more situations, to higher hand models. For example, n equals 3 and n equals 4 can be easily done and simulated. We are working on addition of matter, as I showed you in the sort of in the Schwinger model, for example. And we are also working. There should be a paper coming out very quick in just a short time to study the same kind of model, but for non-abelian discrete and finite group, such as, for example, Dn. And what we are working now, thanks to a collaboration of INFN with the CERN and IBM, to be able to actually to really perform these calculations on the real IBM computer, to which we have access now. Okay. Well, thank you again to all of you for your attention, and thanks to Bal for everything.
Well, thank you very much. Kumar?
Hello, Elisa. This is Kumar.
Hi. Nice to see you. I don't see you, but nice to hear you. Okay.
Right. Thanks for the talk. I have a
Thanks.
question regarding the first part of your talk.
Sure.
So, when you were looking at this Schwinger model,
Mhm.
you said, yeah, right. So, you used DMRG. So,
Yes.
I mean, I was wondering, can you also calculate the entanglement entropy here using some method?
Yeah, sure. I've not shown it here, but we have a very similar plot. For example, for the spontaneous. I might have it. I don't know. Let me see if I put it in the backup material. I think it's not, but it has actually again oscillations. So let me just to describe. Actually, the entanglement entropy has different behavior depending if you are in the weak or strong coupling regime. If you are in the weak regime, you have a monotonically increasing entanglement entropy with the linear first part, as it is predicted by actually conformal field theory. But then if you are in the strong regime, so like here, for example, for m equal 4, then you start to see oscillations, and oscillations are stronger and stronger as you enter as you go deeper in the strong coupling regime.
And did you try that for different quench protocols or just for single? I mean, just some.
I mean, this is just a sudden quench. Okay, so we are actually switching from the Dirac vacuum to the evolution of. We have not tried, let's say, not sudden quench protocols like the one that are used, for example, to study Kibble-Zurek mechanisms in this kind. No, that we have not tried.
My last question is that could you use something like ITBD in this case for that kind of analysis?
Yes, sure. Yeah, just you can.
That change the result from the DMRG. That's my question.
Why do you think it should change the result?
I'm asking, will it for it?
No, I don't think so. I hope not. Okay, it's no. I mean, we tried. We did a small calculation using exact diagonalization up to the length. I mean, just to give you an idea, here we are able to reach hundreds of sites. Okay. And the convergence to the thermodynamic limit is quite fast. So we check that in static situations, not dynamical. And there is, whereas for exact simulation, we can go just to 20 sites at most. Okay. And actually here, the point that we didn't want to stick only to Z2, we wanted to go here, the result I'm showing here are done for that, the one for Z3, but actually we went up to Z7 because we wanted also to check the limit in which the n of the Zn approximation of the U1 symmetry was going to infinity. So we wanted to recover the U1 results of the Schwinger model that indeed we managed to do.
Okay, thank you very much.
Well, are there more questions? I would have just a small question.
Sure.
In the Schwinger model, when you showed this picture of the string splitting in time.
Yes, here. Okay.
So is there a kind of phase diagram that you can get if you study more?
Yes, actually, by just looking at the string, we have it in the paper. I don't think I have it here in the backup slides. We did a sort of phase diagram as a function of M and G, okay? And we don't really have a phase transition, let's say like that. We have crossover regions that go from one to the other regions, okay? So we actually have a region when M and G are small, which correspond to this, let's say, completely breaking and spreading of the excitations, and then an intermediate region that we call intermediate coupling region in which that happens. And also you can see that actually what really matters in all that is a sort of ratio of M over G, okay? Because those are the two parameters that appear in the Hamiltonian. And then in the very strong coupling regime, we have the third one. But we don't really see sudden or abrupt changes from one to the other region, from one region to the other. And we see more like crossover kind of behavior.
Okay, thank you. Sachin?
Hi, Elisa, this is Sachin.
Hi, nice to hear you.
So, is there do you have any physical understanding of why the string is stable at strong coupling?
I think that what's really happening here is confinement. Okay, so the idea that particle, I mean, you have for some reason here the interaction is so strong that we are not even allowed to make a particle move a little bit nearby sites, and they are just kept there. But I actually agree, this is actually quite very interesting. There are some other a more recent paper done by Giuseppe Magnifico, who is one of the guys who was also involved in this work, and now he's in Padova with Simone Montangero, who did the simulation for the same kind of things, actually for scattering of mesons in 2D. Okay, here we can talk about scattering of mesons, and they find a similar situation in which actually they have different regimes. But and this is a very interesting anyhow question to answer. It would really be nice to see what happens. I mean, what seems to happen here that you don't really reach in a asymptotic state in which you have free excitations, right? So everything stays confined here and in a very strong way. There is another thing that somehow struck me, because if I think it classically or semi-classically, I would think that the idea that you let the string evolve freely. So I would expect classically that at a certain point it will start breaking, okay, because the energy grows linearly in one dimension, right, with the size of the string. But classically, I would expect it to break it into half and then in fourth and so on. Okay. Instead, what you see here, that quantum mechanically, it actually breaks immediately into the smallest strings as possible. So just meson pairs. Okay. And then the fact that mesons, two mesons emerge at the end is just a result of interference effect that happens in the middle. I mean, at intermediate times. There's something also that struck me, but I have no physical intuition why that's happening actually.
Yeah, the first picture reminds me of hadronization that the people at QCD talk about.
It could be right. Yeah, right.
I know
so
that
it's really that I just have intermediate small pairs, and then we'll just recombine them with the quantum. This is a really purely quantum interference effect. Okay, and at the very end you see the two mesons. So that's yeah.
So
but I think it's interesting that
curious about the last picture, whether there's any intuitive and any physical understanding. But thanks.
Yeah, I mean, just saying that this is a particle cannot actually move at all, right? And pair production is completely suppressed somehow. Okay.
Well,
because what I see here is that actually have this string breaking mechanism. What happens is that I'm able to create particle-antiparticle pairs inside the string that eventually recombine somehow. Okay, and here this pair production is completely suppressed in the strong coupling regime.
Well, thank you very much, Elisa.
Okay.
Let's talk. So let's thank again.
Thank you to you all, and I hope everything will be fine for you till the very end of the conference.